Guys, here's our last homework assignment for probability. So this is another question using a table. So in part A, what's the probability that the student is studying a language other than English? So basically, we can just add up all of the probabilities here: Spanish, French, German, and all others. The one we don't want to include is the 0.59. So there you go. 41% is that probability. What's the conditional probability that a student studying Spanish, given that they are studying some language other than English? Well, in part A, this is the probability that they're studying something other than English. So essentially, we're limiting ourselves to this part of the table, and the probability they're studying Spanish is 0.26. So we simply want to compare that 0.26 to what we found in part A. That gives us a probability of about 0.63. So here, the key to this question is understanding what the percentages actually mean in the question itself. So 10% of adults belong to health clubs. So the probability of belonging is 0.1. And 40% of these health club members go to the club at least twice a week. So that's a conditional probability because in that 40%, first you have to be a health club member. So first you have to belong. So the probability of going twice a week, given that we know you already belong, that's the 40%. And you're trying to find here what percent of all adults go to a health club at least twice a week. So that's actually an and probability because they have to belong and they have to go twice a week. So we can take the probability of belonging times the probability of going twice a week, given that they belong. This is the general multiplication rule. So those are the two probabilities that we've got, the 10% and the 40%. Gives us 0.04. So here, in this question, we are interested in the probability that the string of lights will remain bright for all 3 years. Okay, so remaining bright for all 3 years, that means that none of the lights fail. All right, so each light has a 2% probability of failure. That means that they have a 98% probability of remaining bright that entire 3-year period. And because the lights fail independently of one another, I can just take that 98%, that 0.98 probability, and raise it to the power of 20. And there we go. We have about a chance of 0.668 that the string of lights will be bright for 3 years. So here, again, in this question, it's important to identify what the probabilities are within the question that you are given. So first thing, what we're trying to find is this. What's the probability that at least one of these people is a universal donor? So at least 1 of 10 is a universal donor. So the way that we can think about that is the one outcome that we don't want is that none of the 10 is a universal donor. So the probability of at least 1 is 1 minus the probability that none of the 10 is a universal donor. So here, the 7.2% of Americans have O negative blood, and O negative blood is the universal donor. So here we go then, 1 minus the probability that all 10 people are not O negative. So look, I want none of the 10 to be a universal donor. This is the percentage of being a universal donor, and I don't want any of them to be a universal donor. So the probability of not being a universal donor, that's 100%, take away the 7.2%. So there's the 0.298 probability. So 1 minus that 0.928 probability, if you raise that to the power 10, now that's the probability that all 10 of them are not O negative, and that's what we were trying to find. So the idea here is when you see the phrase at least one, the probability of at least one is the same as 1 minus the probability of none of that event happening. Well, if I want none of them to be this, then I need all of them to be not O negative, and the opposite of the 7.2% is the 0.928, 92.8%. So I need everybody to be represented by this 0.928. That's why it's raised to the power 10 here. Let's try it again. So lost internet sites. 13% of internet sites referenced in major scientific journals, they're lost within 2 years of publication. No problem. So what's the probability that at least one of them, if we have selected 7, what's the probability that at least one of them doesn't work 2 years later? Well, the probability that at least one of 7 sites is lost or one of 7 sites doesn't work, that's 1 minus the probability that none of them is lost. Okay, the 13% is the probability of being lost. So in this case, I need 1 minus the probability that all 7 sites are available. So to be available, I need to take the complement of this. That would be 87%. So I need to take 1 minus the 0.87 to the power 7. And there we go. It's approximately 0.623. So again, there's that phrase, at least one, 1 minus none. None of the 7 sites is lost. If this is the percentage of the time that they're lost, then 87% of the time they're available. And if none of them are lost, that means all of them are available, all 7. So I can just take the 0.87 to the power 7, subtract that from 1, and we're good to go. So a few questions then in context. Airline reports that 85% of its flights arrive on time. So to find the probability that its next 4 flights into LaGuardia all arrive on time, can you just take 0.85 times 0.85 times 0.85 times 0.85? And the answer is no. And the reason the answer is no is because this expression here assumes that whether the 4 flights arrive on time, that those are all independent. Multiplying in this way implies that the events arrive on time and their arrival on time is independent. So whether one flight arrives on time is independent of whether the next flight arrives on time. And that doesn't make any sense. Think about this. If a flight's not on time, its late arrival could delay the arrival of other flights. And in this case, the flights are on time or not being on time. Those are dependent events. So think about this. If the weather is really good, fine. Then if one flight is arriving on time, then that might make it more likely that the next flight is arriving on time because the truth is the weather's good. Same thing, if the weather's poor, if one flight is late, well, gosh, guess what that does? That means the next flight is late because the first flight had to land first, and then the second flight has to wait for the first one to land. So these are not independent events. We can tell stories that would explain here why we shouldn't be multiplying these probabilities together and acting like they're independent. So the probability of a flush. So here we go. A flush is a hand of 5 cards in poker where all 5 cards are the same suit. So concentrating just on spades, what's the probability that the first card out of my 52 cards is a spade? Okay, well, there are 13 spades out of 52. There's my probability. Now, the next probability is conditional. What's the probability that the second card is a spade, given that the first card was already a spade? Well, there are 12 spades left out of 51. And in part B, if we continue counting in this method, we can find the probability conditionally that the third card is a spade. Well, that's 11 left out of 50. The fourth card being a spade, that's 10 out of 49. The fifth card being a spade, 9 out of 48. Well, here we go. The probability of being dealt 5 spades then, that's the product of the 5 probabilities that we already found. This is the probability of the first spade. And given that the first card was a spade, here's the probability of the second spade. And given that the first 2 cards were spades, here's the probability of a third spade and a fourth spade and a fifth spade. Those denominators changing are telling us that the second, the third, the fourth, the fifth probabilities are all conditional. So we can multiply these together with the general multiplication property. So if you multiply all of that out, this is not a particularly likely hand at poker. It's approximately 0.0005. It's 0.000495. So now think about this. The probability then of being dealt 5 spades is what we found here in part C, but you could also have 5 hearts, or you could have 5 diamonds, or you could have 5 clubs. those probabilities are the same as 5 spades. So there are 4 ways that this can happen. So ultimately, the probability of a flush is that 0.000495. We have to multiply that by 4 because there are 4 different suits in which that can happen. So the probability is about 0.2%, 0.00198, and that's one of the reasons why a flush in poker is considered a pretty good hand.